presentation. Now we are going to present Dr. Diaz Ramirez and the engineer Martin Gonzalez and the engineer matching method.
In this talk, we're going to show the usefulness of the template matching methods applied for robot navigation. So this is the outline. First, we are going to talk about So nowadays, mobile robots are make decisions for navigation. So in this context, the use of vision sensors to perceive the visual environment are very used in this kind of technologies, and also have many challenges to be dealt with. So in the case of vision, path planning, navigation, and the control of the sensors that possess the robot. So in this work, we are focusing on the task of object recognition and target tracking. In order to last talk, we briefly review the concept of object recognition. If you remember, consists in solving basic tasks such as object detection, object localization, and classification of the detected objects. Additionally, the problem of object tracking consists estimate state trajectory of an object of interest while it's moved through a detection zone. So perform reliable object recognition, we need to perform an estimation of its trajectory or any other state, such as pose or velocity, any other characteristic of the object. So for the task of object tracking, there are many challenges that we need to deal with in order to design or to create an efficient and useful algorithm. For instance, the presence of noise and of non-uniform illumination, occlusions, and also real-time requirements. So a tracking algorithm must be robust, accurate, and fast. Within the state of the art of this kind of techniques, there are many well-known techniques used for the detection and descriptions of objects in the environment that the robot needs to detect and describe to perform a navigation task. For instance, the scale invariant feature transform or the speed up robust feature that detect and describe points of interest. tracking, learning, detection. This is also known as a predator algorithm. This is very well known. And others, for instance, the robust object tracking with online multiple instant learning. These algorithms have in common that once the object of interest is defined, the algorithms learns as the time passes. So it becomes more. Here in Citedi, we propose the use of the template matching approach to design a tracking algorithm applied for robot navigation. So in this approach, we need to design a match filter, but this filter needs to be dynamically adaptive to each capture frame of the scene, whilst the robot is in motion, and takes into account the current and past estimations of the target of its interest. It's tested on the navigation of a mobile robot. So in the past presentation, we briefly reviewed this process of object recognition by template matching. By remembering, we have an input scene. We transform to the frequency domain by the Fourier transform. We multiply it by a frequency domain filter. This is the match filter that we need to be designed. And the filter spectrum is converted to the space domain through the inverse Fourier transform. And then we search for the maximum intensity value, the location of the maximum intensity value, and this is taken as the estimates of the location of the coordinate of the target in the scene. And then if this intensity value is rejected. So for the case of object recognition in realistic scenes, we use this signal model, which consists of an object of interest located at unknown coordinates, which is embedded on a disjoint background, and the whole scene is corrupted by additive noise. So in this case, we need the description of the target, the region of support, and some information of the background and the additive noise. When we process images in color, a widely used approach is to process independently the three channels, the three color channels. So in this case, we can apply a color codification of the three color channels into a single channel by using complex numbers, like this codification. So this allows us to process color images in only single channel. Allows to recognize multiple views of a target with a single filter. So the proposed method is based on the MOST filter, which minimizes the output sum of square error of the multiple views of the target to be recognized, and a predefined output filter. So this is the expression for this filter. So this is the block diagram, and starts with the initialization process, in which a capture frame of the scene is acquired by the camera, and then the target is selected by the user. And then we perform the color codification. Then with this information, we construct the MOST filter, and then capture a new frame, perform the color codification, and apply the construct filter to the capture frame in order to detect and localize the target. Then after a few frames, we can perform a prediction of and then we adapt the filter for this new information, and this loop is continued for each coming frame of the scene. So this is an experimental demonstration of this approach. There's some preliminary information. So the first step is to manually choose, in this case, of the target object. In this case, is the face of this subject. And then we construct an adapted filter like this one. You can see how the template is target change in pose, scale, rotation, any other degradation, and this is the output of the filter. By remembering that the location of the maximum intensity value is the estimates of the coordinates of the target in the scene. So we consider handling of occlusions, and we test this algorithm on real images taken from a very challenging database, and we compare the performance with different. It's named in this video like dynamically adaptive correlation is the red square. The white is the ground truth, and the blue, green, and yellow some existing methods. So you can see that the proposed filter is very robust and accurate in estimating the location of the target in the scene. Here we can see many different and challenging situations, and the proposed algorithm works well. Okay. For instance, here we see a very difficult conditions of scaling and deformations. Okay.
To test those algorithms, we made an experimental platform. We use AmigoBot from Adept Mobile Robot, and we built a case for the brain. We use NVIDIA Jetson TK1. We use the library area for programming this platform. We use the language Python and OpenCV to write the code, to write the algorithms. And we use a Logitech webcam. So we designed a platform. We made this test inside the laboratory. As you can see, the robot is tracking the vest, the jacket, and the tracking is based on the color and the shape of this vest. It has a simple PID that allows us to control the movement of the robot. Outside the laboratory to make a more realistic test. And this video shows the parts and all the process. We have the parts, the Jetson, the camera, and we have the visualization of the robot, how it works in the practice. we can change the color and the reference, and the algorithm is going to work perfectly.
Basically, this task consists on capturing visual information and describe this information. Well, one of the solution proposed on the literature is assume that we have a planar scene observed. In this case, we can the homography can be represented by a perspective transformation. In this picture, we can observe the planar surface and two observation planes, and one point observed. These points can be described by homography transformation. On this image, we can observe the same object with different. We can recover the estimation by homography. The homography is represented by a matrix, the 3 by 3. These four represent the rotation parameters. These represent the translation, and these represent the perspective transformation. Can be defined by the intrinsic and extrinsic parameters of the camera. Basically, the intrinsic camera parameters is the focal length, that is the distance between this camera center and the image plane, the pixel width, pixel height, and main points. And the extrinsic parameters, its coordinates and the camera coordinate and the translation. Actually, we propose an algorithm to estimate the homography using template match technique. That we start with image, input image, detect visual information in the input image, extract feature characteristic, and matching between the input image and feature of reference. When are matching, we generate candidate solutions that consists on homography. We transform the input image with the candidate solution. This image transformation performance of this filter. This process will repeat a number of iterations. Finally, obtain the homography parameters to obtain the rotation and translation values. And in this picture, we can observe the input image. And in the second image, we can observe red dots that are the feature of reference. With this feature of reference, make the correlation filter. In this picture, we can observe the input image, the image of expression of the reference features, and a difference of image transformation with this candidate solution. we can observe the correlation plan. That extract the reference fixtures. Well, conclusion: an algorithm of object recognition and tracking based on template matching filter was presented. The algorithm is dynamical, adaptive to each captured frame, and no previous training process is needed. Several components match filter were evaluated. The most filter was identified as feasible option. The performance of algorithm was tested in synthetic image sequence in terms of the objective measurement, and the successfulness of the proposed algorithm was verified experimentally on a mobile robot.
Questions and answers. Does anyone have any questions for the speakers?
I have a question. You can modify the algorithm to make like a search sign, like a path, and put in the robot another accessory, you know, to shoot something.
At the beginning of the tracking, in this algorithm, you need to select the object of reference, and then the algorithm starts to follow and capture information of the different views of the object, and learns to try to follow its trajectory more robustly. So if you want to use it for another application, you need to restart the algorithm and choose a new. Okay.
Well, it's a very interesting work. Regarding to the human following robot, when the robot loses the reference in the corridor at the corner, how does the robot know to turn to the left or to the right?
Okay, well, the robot is tracking the object. It only processes a small object. When the robot loses the target, it starts to follow in the whole scene, and when he recaptures, then we start again to track the object. But this is more or less the strategy that we use.
Okay, and so at that moment the robot stops and looks around the image for the reference, and when he recognizes again the reference,
Yes, he starts to turn. He sees it again. It restarts the tracking.
the camera, only one camera is the only sensor.
Mhm.
Is the unique sensor.
Yes.
Thank you.
Okay, thank you.
Anyone have another question?
Martin, when you perform the perspective correction, you said that you need to select some key points in the scene. How did you select, or how did you choose?
Actually, we select major information is where the key points is present, and actually this is the methodology used. We need to improve this method to become the algorithm robust.
Do you think that there's any possibility that the algorithm might be able to track more than one object at the same time? Yeah.
Yes, this test of multiple objects has not been done yet in the mobile robot application, but we have a simulation of only the tracking algorithm for tracking like a complex correlation function, and we code a specific phase value for different objects, and this allows us to detect both and to assign each one to the corresponding category.
Thanks.
Anyone have another question?
Why can you can bring the robot to make the demonstration here?
Yes. The main limitation Citedi at the night when the traffic of the web is low. So this is the main limitation. But anytime we can program a demonstration if you want.
Thank you.
Okay, anyone, another question?
This is the maximum distance the robot can track the object.
The precise, it depends on different factors. For instance, the length of the camera and the speed of motion of the robot. But in the test that we done, we made, I think like 10 or 20 meters is the range of correct functioning of the tracking.
Does any have any other question or anyone? Dr. Diaz, Martin, and Mac.
Muy bien, equipo.
Sí.